my cursor as well?
Yes, yes, we
Yeah.
see. Mhm.
So, hello all. I am Vishwajeet Kumar, a PhD student at the Institute of Mathematical Sciences, India. Firstly, I want to thank the WOST V organizers for giving me the opportunity to present my work here. In this talk, I would be delving deeper into the Arrhenius law for interacting diffusive systems by drawing results from our two recent publications in Physical Review e-letters and in the Journal of Chemical Physics. So here is the contents of my talk. I will first give the motivation and background for our research. We'll then move on to the central question that propelled us to our investigation. I will then describe the models and the setup, and will finally reveal the results that we got. Okay. So after analyzing several chemical reactions data, Arrhenius came up with an empirical formula governing the rate of chemical reaction, which is given by this particular formula, where EA is the activation energy required for a chemical reactions to occur. So a chemical reaction is often schematically represented by the plot by the schematics here, where the reactants need to be supplied with an activation energy so that it can form a product. So Arrhenius law is often manifested within the Kramer's reaction rate theory. So where he considers the following. So consider a Brownian particle trapped in metastable state of a potential landscape, and it has to overcome a barrier of height delta U in order to go to another metastable state of the potential landscape. So when the height of the potential barrier in front of the Brownian particle is much greater than the thermal energy available to the particle, Kramer showed that escape rate is given by this particular formula. One can at once see the striking similarity between the Arrhenius law and the Kramer's escape rate formula. And in what follows, I will interchangeably use the word Arrhenius law and Kramer's escape rate formula. What is so special about Kramer's escape rate formula? So we can see that the exponential term in the Kramer's escape rate formula only depends on the height of the potential barrier confronting the Brownian particle. It doesn't depend on any other intricate details of the potential landscape. For example, it doesn't depend on the curvature of the potential landscape. So it is this universality that has attracted researchers over the years, and people have investigated this universality in case of complex systems as well. But will the universality hold in place of complex system? People have investigated some of the complex systems and found that the Arrhenius law actually breaks down in case of active particle system in low temperature glassy dynamics and in infinite range interactions. After this small background, I now move on to the central question that we ask. We ask that what happens to this universality in case of interacting diffusive systems, and what is the corresponding generalized Arrhenius law for such a system. I now move on to describing the model. The first model that we considered is of simple exclusion process. So simple exclusion process is a lattice gas model where particles on a lattice can jump to its nearest neighbors given the target site is empty. Also, so this particular dynamics of the particle hinders it to sit on top of each other. So that means a single site can be occupied with at most one particle at a time. The other model that we considered is of zero range process, where a site can be occupied by any number of particles, and rate of jump from a site to another site depends on the number of particles from the departure, number of particles on the departure site only. So I will now describe the setup with the help of an example of simple exclusion process. So we consider a system of lattice gas of size capital L. We invoke a reflecting boundary at initial site and an absorbing boundary at the last site, and we put all this whole system into an external monotonic potential. Now, large system size, one can do diffusive rescaling, and which means that the the site variable I will be now replaced by the continuous variable X, and this whole system will look something like this, where now we have a reflecting boundary at X equal to 0 and an absorbing boundary at X equal to 1. So what is the question that we are asking here? We are asking the question that what is the escape rate of the fastest particle? By this, I mean, what is the absorption rate of the first particle that gets absorbed at X equal to 1? So to find the answer to this question, we employed the macroscopic fluctuation theory. And in this slide, I will be describing in brief what a macroscopic fluctuation theory is. So the two models that I described can be described by fluctuating hydrodynamics, which consists of a continuity equation in the density and current of the system, and the current has two terms. Basically, one is the fixed term and the other is noise term, and this noise has mean 0 and it's delta correlated in space as well as in time. Also, one should note that the strength of the noise depends on the mobility of the system. Also, as I described in my setup, that we have a reflecting boundary at X equal to 0, and this translates to the current being 0 at X equal to 0, and absorbing boundary at X equal to 1 translates to the density being 0 at X equal to 1. Now one can use the Martin-Cziarow's formalism to find the probability of observing a particular density and the current profile. And now, after having got this probability, one can find the survival probability of all the particles. So we want all the particles to survive, and this will be given by conditional sum over all paths. So why conditional? Because this should satisfy the boundary condition, the reflecting boundary and the absorbing boundary. And also, since we want all the particles to survive, the particles number should also be conserved. And now the large system size limit will help us to take a saddle point approximation, which automatically leads to a non-linear Euler-Lagrange equation. So by solving this non-linear Euler-Lagrange equation, one can find the survival probability of all the particles to survive. And from there, one can infer what is the escape rate of the fastest particle. So after having described this macroscopic fluctuation theory in brief, I now move on to results by skipping further technical details. So we saw that for the models that I described, the result can be combined in one simple formula, which is here. And we noticed that there is an extra term which was not there in case of single particle Kramer's escape rate formula. What is this rho 0 bar? It is basically the mean density of the system. Also, one thing to note is that when G is less than 1, the escape rate is enhanced. So now I discuss the result model by model. So first model is the simple exclusion process, where we found that this G is actually 1 minus U at rho 0 bar over delta U. So please see this plot where we have taken three different potential landscape: linear, harmonic, and cosine. And consider, for example, linear potential landscape shown by this orange plot, where we have taken this potential to be delta U times X, and we get that G is equal to 1 minus rho 0 bar. Similarly, for harmonic potential, we get G equals 1 minus rho 0 square. For the other model that I described, the zero range process, we get G exactly equal to 1. So this is all I wanted to talk about my work. Finally, I want to acknowledge my supervisor, Dr. Arnab Pal, and my collaborator, Dr. Ohad Spielberg, and my funding agencies, DAE and Homi Bhabha National Institute. Thank you.